thank you very much once again. I guess now I will introduce our next speaker. So the next speaker is Ben Zinberg from the Massachusetts Institute of Technology. So Ben, you should turn on your camera, your microphone. Yep, perfect. Thank you so much.
Can you hear me?
Yes, I can hear you, and I can see you.
Okay, so I'm gonna share my screen to show the slides. One moment. Okay, and so yes, as with Leslie's case, once I go to the slides, I have no visual feedback. Please talk to me if something's wrong. Okay, great. So I'm going to be presenting on structured differentiable models of 3D scenes via generative scene graphs. This is work with Marco Cusumano-Towner and Vikash Mansinka. Okay, so I'll start with some of the broad motivating problems we're trying to make progress on, and then I'll briefly discuss prior work that uses similar approaches. Next, I'll introduce the central knowledge representation we're using in this work, which we're calling generative scene graphs. After that, I will, sorry, 1 second. Technical difficulty, 1 second. Lost the screen. Just a moment. So after introducing the knowledge representation, and I'll talk about some of the infrastructure we've built around it. After that, I'll walk through a concrete example of modeling inference of generative scene graphs using the Gen probabilistic programming system. Next, I'll briefly describe some of the applications we're pursuing, some other applications we're pursuing, and finally, I'll describe some extensions to the scene graph concept that we think will be useful directions for future progress. Okay, so yeah, so broadly, our motivating problem is engineering common sense about physical objects. And it's probably worth saying this problem is so broad that most people view it not as not one, but a million open problems, right? So like one for each of the different subtasks that sort of common sense would enable. So we're certainly not solving this problem. We're like only taking a very small step. But a few facets of this problem that I'll touch on, especially in the talk. So one is that, so given that state-of-the-art computer vision is unreliable, we want to make systems that work reliably even when vision is unreliable. Another aspect, we want our AI systems to be able to incorporate prior knowledge about which scenes can occur, not just which scenes are physically possible, but also distributional knowledge about what kinds of scenes tend to occur. Not sure if this is blocked by the Google Slide Present thing. See if I can move this. Well. Okay, so the third is that we'd like to engineer synthetic test cases for AI systems to exercise difficult scenarios and cover the long tail of some unusual but important cases. And finally, we'd like to understand which knowledge representations give rise to robust performance in a variety of environments. So those are some of the key motivating problems. So I'm going to move on to a super quick overview of some prior work. There are a few different ways scene graphs have been used in AI. So there's an approach of using scene graphs as latent variables in order to perform scene understanding, as is done in the work shown on the left-hand side. These are just some examples of such work. And there's also the approach of using scene graphs for generating structured synthetic data, which is done on the right-hand side, work shown on the right-hand side. There's tons more, there's tons more work than is shown here. So for example, Leslie Kaeldling, who just gave the keynote, her group has worked on state estimation in what are essentially scene graph models. And another example, Daniel Ritchie has worked on constrained scene generation and procedural graphics models, which is similar to the inference example, one of the inference examples I'll be showing later in the talk. Yeah, and I guess the work that, the approach that we've been taking of the things shown in this slide is probably closest in spirit to the scene grammars work by Izad and Tedrake, due to we were basically working with latent geometric scene graphs. Okay, by the way, so a note on scalability. In this work, we're working with small scene graphs having just a few objects, and the objects have simple geometry, because that's the stage the work is currently in, though we do think the ideas will scale in principle. So for comparison, the use of scene graphs in graphics and game engines did scale, but it took decades of hard engineering work to make that happen. So the use of scene graphs in AI is still at an early stage, and it's going to take time. And we're only making a small step here, very small. But it is worth noting, though, that these small, low-resolution graph representations are often useful. So it's just an illustration. You can see on the left here a simplified car model. This is coarse and very low polygon count, but it is a useful understanding of the scene, even though it's not as high resolution as the model on the right. Another note on existing work that's been very beneficial for us. In this project, we used an extensible probabilistic programming system called GEN, which was developed in our lab. I'll mention a few of the key features of GEN that made this work possible. So first, GEN gives the user fine-grained control over the inference algorithm. There's an extensible library of building blocks for implementing efficient custom inference strategies at a high level of abstraction. And second, GEN supports gradient-based optimization using automatic differentiation, which is useful for, well, gradients are useful for inferring and fine-tuning pose estimates. And third, GEN has strong support for reversible jump MCMC, which is a really, really key tool for inferring scene graph structure. Okay, so now I'll describe what generative scene graphs look like and what they mean. So I'll return to this slide in a bit, but for now, just to say, we've built a bunch of infrastructure around the scene graph representation. So before talking about that infrastructure, I'm going to start with a simple example to illustrate the concept. Okay, consider this scene of 3 blocks stacked on the floor. One way to represent the scene as a scene graph is to have no structure. So each object just gets a full 6 degree of freedom pose. But a second way we can represent the scene is as a scene graph that does have structure. So the edges in the scene graph, the generative scene graph, represent contact. So for example, the green block is in contact with the floor. And if you, given that there's a contact there, there's actually only 3 degrees of freedom for the relative pose of the green block on the floor, right? There's a translation, you can sort of move it around in the XY plane, and there's a planar rotation for the relative orientation. And similarly, the red block is stacked on the green and the yellow block is stacked on the red, and these each have contact edges, and their relative poses also have only 3 degrees of freedom. If you want, you could also combine that with some prior knowledge about the floor, such as the floor is flat. That might knock off a few more degrees of freedom. And in the end, what you get is this structure representation number 2. If you put the right structure on your scene, then the parameter space has significantly lower dimension than in the unstructured representation, right? 12 parameters versus 24. To say this another way, to illustrate this kind of in another way, we can say that, like, rather than looking at the full space of all scenes, which includes a lot of scenes that are clearly impossible as depicted here, if we know the scene graph structure, that allows us, well, yeah. So that allows us to look at just like a subspace of interest. So it is true that the combinatorial search for scene structure is hard, and we'll return to that later. But if we know the structure, we get an easier search problem in the parameter space. So for example, these blue scenes, sort of schematically shown as points on the blue curve, correspond to examples of the stacking structure I showed on the previous slide. And we can consider other scene graph structures, other stacking structures, right? So the magenta curve is a different arrangement of the blocks, and the scene graphs are as depicted here, right? You've got the magenta scene graph shows the green block on the floor, the red block also on the floor, and the yellow block on the red block. Yeah, so it's worth also noting that the computation of the absolute pose of the 6-degree of freedom pose of an object is differentiable. So here I've repeated this blue scene graph, the stack of blocks, and I've denoted the contact parameters along each edge. So floor to green is kappa 1. Those are the 3-degree of freedom contact. Similarly, kappa 2 and kappa 3 for the other contact edges. And if we want to differentiate the yellow block's pose with respect to the floor's pose and the contact parameters via the chain rule, we essentially just multiply Jacobians along the graph. More than that, though, our implementation of generative scene graphs in Gen has the property that the whole end-to-end system is differentiable code, which can then be used with automatic differentiation. So namely, on the very left of the slide, Gen supports auto differentiation of the joint log probability density of a state with respect to both the inputs to the model and the values of random choices made in the model. Next, as we showed in the previous slide, the computation of relative poses is also differentiable. And after that, well, it depends. There's a variety of components you could hook up to the scene graph, and your end-to-end system will be as differentiable as your component is. For example, if you have a differentiable renderer, then you can differentiate the image. Or you can use an arbitrary objective function as long as you're, and as long as it's differentiable, you'll get end-to-end gradients. It's worth mentioning, by the way, also, another kind of geometric calculation that our infrastructure supports, and it's often useful when modeling physical scenes. And that's two things: detecting when objects interpenetrate, when they overlap, as Leslie was talking about. This is a tough problem to get rid of, and detecting when objects occlude each other. Both of those calculations are done. They may seem like different calculations. They are different calculations, but they're done in a similar way. We just use an off-the-shelf linear programming library because we're approximating objects as their bounding boxes. So I've sort of illustrated how it goes in this picture. I won't go into full detail, but this is an example of the idea I said before with the car model that low resolution approximations can be useful. In particular, here we have a rough calculation of occlusion that's much cheaper than computing the exact answer, which would require a full render of the scene. So this strategy is probably, in some cases more suitable for being in the inner loop of a model that we're doing inference on and may have to run the model many times. Okay, so returning to the infrastructure, there are a number of other features supported in our library, notably an extensible object library that includes both simple geometric shapes and YCB meshes of household objects like mustard bottles. And we have a PyBullet-based renderer for debugging and also useful for data generation. And importantly, we can plug these occlusion calculations that I was just talking about into Gen to explicitly model occlusion and use inference to enforce constraints against implausible scenes where objects interpenetrate. Okay, so let's walk through a concrete example of modeling and inference using generative scene graphs in Gen. We'll see both how to write a prior distribution on scenes as a model in Gen that produces samples like these. So these examples, this is 3 samples from a prior of stacks of objects on a table. And I show on the top with the camera being this blue box looking down on the scene, and on the bottom is the camera's view of the scene. And I've highlighted sort of baddies. I've highlighted instances of interpenetration. So these are not, the prior doesn't, the prior that I'm going to talk about doesn't enforce non-interpenetration. We'll use inference for that. There's not interpenetration of the table, but nothing is stopping the objects from interpenetrating each other. And so let's talk about how we can use inference to enforce constraints. And the example constraints that I'll use are no interpenetration. And this is kind of arbitrary, but let's say we want a sugar box to occlude 50% of a Jell-O box that's on top of a meat can. So we have a desired like amount of occlusion. Okay, so so let's see in more detail how this could be done in generative scene graphs. But no need to sort of go into every line of the code, but I'll just say the number of stacks of objects in this model is a Poisson random variable, and the identities and relative poses of the objects are chosen randomly. And this information is put into a generative scene graph, which is the return value of the model program. Okay, so the next question is, how do we enforce the constraints? And what we do here is we introduce likelihood penalties. We wrap this unconstrained model in an outer model which inspects the return scene graph and checks whether it satisfies the constraints. And we define penalty terms during inference that we observe to be 0. So in other words, this observation will be very unlikely if the constraints are violated, and this pushes the posterior towards satisfying the constraints. So you can see here we have an interpenetration penalty whose mean is insanely high. It's, well, compared to the variance here, if there is interpenetration, and it's 0 if there's no interpenetration. Similarly, we draw a noisy occlusion fraction and we observe it to be the desired value. So here we observe the sugar box and the jello to have an occlusion frac of about 0.5, 50%. Okay, so let's see inference in action. So here's an example of an inference program. So I guess I should say a couple of things about why this kind of inference program is useful. So as is often the case, generic Monte Carlo inference will be too slow. However, gradients alone don't work either. So like, for example, say we start in a state where no objects interpenetrate, but the meat can doesn't include the jello at all. In that case, the gradient we need to get us to closer to the 50% occlusion fraction will be 0. So we do have to actually use some non-local search. And so the strategy we use to fix this is by starting with Monte Carlo and moving to gradients once the occlusion fraction is non-zero. So you can see this inference program has 3 loops. The first loop uses drift MCMC to perturb any objects that are interpenetrating and runs until the interpenetration is gone. The second loop uses a combination of drift MCMC and resampling from the prior to adjust the position of the jello box until it's occluded. So it'll do like a random walk, and it'll continue until it's occluded at least a little bit by the sugar box. And then the third loop uses gradient-based map estimation to fine-tune the poses of the sugar box and the jello box together to reach the required level of occlusion. And to see a video of this algorithm running, well, I'll play it here. Hopefully it comes through. We see the de-interpenetration of that sugar box, and then the meat can wanders around. It's gone off the edge of the viewing window now, but it's coming back. And now gradients are moving these things closer together, and you can see the jello box is getting more and more occluded until it reaches 50%. Play that one more time. De-interpenetration, random walk, and finally, once there's any occlusion, like here, they start moving closer together. The other video is the same thing from the different viewpoint. Okay, so now that we've seen an example in some detail of modeling and inference using generative scene graphs, I'll briefly describe some other ongoing work in our lab that uses the scene graph representation. So first, I'm perceiving 3D scene graphs to improve noisy neural detection.
You have 3 minutes.
So the problem sounds good. So the problem here is that there are these errors that occur with state-of-the-art neural detectors that you can see there's flicker, right? The green box kind of explodes. So some frames are unreliable. And the strategy that we take to fix this is to infer a scene. Infer a scene graph for each frame of the input, the sense data, the video, and put a dynamics model on the scene graphs, basically saying they don't change much, right? So then it naturally falls out of the posterior that a detection error is a more plausible explanation of a flicker frame than that the scene graph actually like severed all edges and immediately reconstituted them. So you can see if we do posterior inference with the latent scene graph, on the bottom we see the structured representation allows us to not have a flicker frame. See the flicker on top, but not on the bottom. Okay, so another, okay, so just to briefly say here, the way that we infer a scene graph on an individual frame makes heavy use of reversible jump MCMC, and Gen has really good support for that. It has a domain-specific language for writing these moves, and the appropriate Jacobian is computed by auto differentiation. So it's very ergonomic in Gen. One more application I'll talk very briefly about, grounded natural language understanding. So here there's ongoing work to produce utterances that describe a scene. So the scene graph is converted to a set of relational statements that hold in the scene, such as object A is above object B or object C is a cube. These relations are converted to formal logic statements and then finally to utterances in natural language. And there's also, we're beginning to explore the opposite direction too, though it's still in the very early stages. So parsing natural language descriptions of scenes and inferring a posterior distribution on scene graphs that satisfy those descriptions. Okay, so we've discussed a few examples of uses of scene graphs. I'll wrap up with a few future research directions. So again, I'll reiterate, our understanding of where scene graph representations should fit into AI systems is still in very early stages, and our work is only a small step. So listed on this slide are a few of the extensions to the scene graphs framework that I think will be useful in future work. Okay, thanks for your attention.
All right, thank you very much. Okay, so we do have a few questions. So I will just pick the questions that have the most votes. Could you expand on your point about differentiability with respect to contact parameters? Won't there be discontinuities when modeling contacts?
Oh, yeah, so there are a couple of places where you might be thinking of discontinuities. So one is the question of when two objects are in contact, let's say my hands are the objects, they have finite extent. One question is, how do I, do I parameterize the contact so that I can't actually, like, this doesn't count if I'm like on the same plane, but on the infinite extension of the plane, but not actually touching. And we've actually tried both approaches. We're mostly using the approach where this is allowed, and it's the inferer's job to make sure that the objects are physically touching if needed. So there are edge cases there.
Okay.
Yeah, I'd be happy to talk more about it offline. The second class of discontinuities is, well, objects have different surfaces, right? This cup has a bottom and it has this curved face here. So that there's edges here where this is like this is like a corner or an edge of the like manifold or whatnot. We talk about contact in the way that we're currently framing it. We talk about contact as being between two surfaces of objects. So if this can be, the bottom of the cup can be in contact with the top of the table, or the side, the curved surface. I'm not going to do this because it'll spill.
All right. So at the risk of running slightly late, there is a very good question I'd like to ask. If you could just give a very short, short and sweet, short and crisp answer. What kind of enhancements would have to be made to PPLs so that one doesn't need to manually loop over different MCMC runs interleaved with checks on occlusion percentage?
Oh, that's a really good question. I think the answer fundamentally is that the inference program will always be necessary, because they're kind of my intuition here, which is a lesson that we've learned since church, is that generic black box inference engines might not be possible. We might really need application-specific.
All right, thank you very much, Ben. And now I'm going to introduce our next speaker. Actually, the speaker is not here, so